Hey Phys 1 kids, Mr. Consolino here. We're going to be working on problem 58 on page 27 in your packet. It's about rotational motion and rotational energy. So the problem basically states that a 34.2 gram marble rolls down from rest down a ramp that loses 6.7 centimeters of height. So if we were just to draw this out of the picture, we have our ramp here that has height h, which in this case is going to be the 67.5 centimeters. And it rolls all the way down that ramp until it gets to some end distance here. And we're going to call the actual length of the ramp here L. And that's going to come up in a later part of the problem. And our marble is up here. And our marble has some mass M. And it also has a radius that we're just going to call R. And in the problem, I believe that gets brought up in part D. So for part A, we want to know what the final velocity of the marble is. And in this case, we're going to use conservation of energy. So we have our initial energy is equal to our final energy. Initially, we're at the top and we're not moving, so we only have gravitational potential energy. So in this case, our initial energy is just equal to mgh. Finally, though, we have all kinetic energy, but because this is a marble and it's rolling, we're going to have rotational kinetic energy, which will be 1/2 I omega squared, plus our translational kinetic energy, which is going to be 1/2 mv squared. So before we move on, we're going to have to determine what the moment of inertia of our marble is. And in this case, the marble we're going to assume is a perfect sphere. And our moment of inertia is going to be equal to 2/5 times the mass of the marble times its radius squared. So we're going to go ahead and plug that into our formula. So we have mgh is going to be equal to 1/2 times 2/5 times mr squared times omega squared plus 1/2 mv squared. The first thing that we're going to do here is we notice that mass cancels out of all of our terms because it appears. So that's always nice, very exciting. I always enjoy when that happens. Our next step is we want to find out what the final velocity is, but we don't know what omega is. But there's a way that we can write that in terms of our velocity. So we're just going to rewrite omega as v over r and get a final sort of energy equation that looks sort of like this. And I'm going to combine the 2 and a 5 here into a 10 to make it a little bit easier. Times r squared times v over r squared plus 1/2 v squared. We're going to simplify this a little bit further. We get gh is equal to 1/5. Our radius cancels out, which is super nice, times v squared plus 1/2 v squared. These cancellations are similar to what we saw in class today whenever we were looking at moments of inertia and how it doesn't really depend on the size of the sphere, just as long as it's a sphere, the radius is going to cancel out. From there, we can combine these two terms here, and we have gh is going to be equal to 2/10 v squared plus 5/10 v squared. And we're going to keep simplifying this until eventually we get what we want, which is the velocity. So we get 7/10 v squared. We can multiply over by 10 and divide by 7. And we get a final velocity that's equal to 10 over 7 gh. And we take a big old square root of all of that. And that is our final velocity for part A. So we're going to keep that in the back of our mind. So we're going to keep that in the back of our mind now. So we're going to write it up here at the top. Our velocity at the end of the slope is going to be equal to the square root of 10 over 7 gravity times height. Now for part B, it is asking what is the rotational kinetic energy at the bottom of the slope. And in this case, all it wants to know is what Kr is. And we know that that is equal to 1/2 times the moment of inertia times omega squared. But we don't know what omega is. But early in the problem, we found that our moment of inertia is equal to 2/5 mr squared. And we're going to go ahead and plug that in here. And we know that omega is equal to velocity divided by the radius. And we know what our velocity is. So in this case, we can simplify our kinetic energy to be equal to 1/2 times 2/5 times mr squared times v over r squared. Sorry, it's getting a little cramped there. Now we're going to go do some simplifications. Both of our 2's cancel. And in this case, the radius cancels out, which is super nice. So here we're left with 1/5 times the mass times the velocity squared. Notice here that whenever we're calculating just the kinetic energy, the mass does not cancel because we're not using conservation of energy. We want to know just what the one individual energy is. And in this case, mass is important. Now all we have to do is plug in what v is, and our velocity, as we found above in part A, is going to be the square root of 10 over 7 gh. So we have 1/5 times the mass times our velocity squared, which is the square root of 10 over 7 gh squared. We can simplify all that down, and we get 1/5 times the mass times 10 over 7 gh. We can simplify this further, and we're left with 2/7 times the mass times gravity times height is equal to our rotational kinetic energy for part B. And you can go ahead and plug in the numbers if you want to. The answers are in the back, but as you all know, I absolutely hate numbers in physics, and symbols just make everything so much nicer. So that's going to be our answer for part B. Is we have 2/7 mgh is equal to our rotational kinetic energy. Now we're going to move on to part C, and all part C is asking is what the translational kinetic energy is. So in this case, part C, it just wants to know what the translational kinetic energy is. And this is going to be really easy for us because we know that our translational kinetic energy is just equal to 1/2 mv squared. The only thing we don't know in this case is velocity, but we found that out in part A, so all we have to do is plug that in for velocity. We get our kinetic energy, translational kinetic energy, is equal to 1/2 times the mass times our velocity squared. Whenever we simplify this all out, we'll find that it actually comes out to be a very nice number. And we end up getting 5/7 times the mass times gravity times height is equal to our kinetic translational energy. And the cool thing here is that we can actually, whenever we add these two together, so earlier we found out that our let me rewind a bit because that was a little confusing. We found out that our rotational kinetic energy is actually equal to, what do we find? 2/7 times the mass times gravity times height. And we know that our final energy has to equal our initial energy, which has to equal to mgh. And if we actually do the math, because we know our final energy is just going to be equal to our translational kinetic energy plus our rotational kinetic energy, we find that 5/7 mgh plus 2/7 mgh, sorry about that, is equal to 7/7 mgh, which is just equal to mgh, which is equal to our initial energy. So that's one way that you can sort of check yourself in these problems if you're ever doubting what your answers are, is that you want to take all your energy at the end, and whenever you add them up, they should equal whatever we got in the beginning. So that's just a nice quick check. Once again, you can always feel free to plug in numbers. I'm not going to take the time to do that because I feel comfortable with these symbols, and symbols are so much fun, and numbers are just horrible, and they make things so much more complicated than they need to be, I think. But if you like numbers, feel free to go ahead and plug in. So the last part is part D. And this is where we kind of combine energy and kinematics together. We basically want to know what the angular acceleration of the marble is as it moves down the incline. And it gives us what the radius of the marble is and what the length of the track is. So that's length r, and the radius of the marble is what we use to calculate the moment of inertia. But in the previous problems, they just canceled out, which was really nice. But now we want to find out what our angular acceleration is, which, if you remember back, is actually given the symbol alpha. And there's a couple ways we can do this. Some are more complicated and some are not. But we're going to use the linear relationship that we know that alpha, or the angular acceleration, is equal to our linear acceleration divided by whatever the radius of our object is. Because this is actually going to be the easiest way to get it. So now instead of having to find angular acceleration, all we have to do is find out what the linear acceleration of our marble is, because we know everything else. We know what the radius of the marble is. So once we know acceleration, we can find out what the angular acceleration is. And the way that we're going to do this is we're actually going to use, I believe it's a third kinematic equation, because we're going to end up using our velocity squared is equal to the initial velocity squared plus 2 times the acceleration times our change in x. So in this case, we're going to look at all of our variables. We know what our final velocity is because we calculated that out in part A. And that's just the square root of 10 over 7 gh. Our initial velocity is really nice. It's just 0 because we're starting from rest, so we don't have to worry about that at all. 2 is a constant. We're solving for A. xf minus x naught. So that's our final position minus our initial position. That's just how far we're traveling. And because we're rotating our axis, the length that we're traveling in this case, it's just going to be length L. So xf minus xo is just going to be length L. So in this case, we can plug in what we know. For velocity, that's just going to be the square root of 10 over 7 times gravity times height squared is equal to 2 times the acceleration times our change in distance, which is going to be L. From there, all we have to do is solve for A. So we're going to simplify this first, and we get 10 over 7 GH has to be equal to 2A times L. We divide by 2L on each side. And in this case, the 2 and the 10 are being divided by each other, so we get 5 over 7 GH divided by L. I'll write that a little bit nicer because it's kind of confusing to see, but basically these cancel out here, and we have a linear acceleration of 5gh divided by 7L. So that's our linear acceleration. In order to find the angular acceleration, all we have to do is we take our linear acceleration divided by the radius, which in this case is just going to give us 5gh divided by 7L times r. And that is equal to our angular acceleration. There are other ways you could go about finding this, but in order to do that, you would have to find out things like the angular velocity and maybe even look at time and stuff like that. So this isn't the only way. This is just the way that I chose to do it. So there's other ways as long as you get to the same expression. And as always, you can plug in numbers if you wish, but we're just going to leave it at variables because I'm sure you all know how to use your calculator. So I hope you all have a wonderful snow day and that the problem wasn't too confusing for you. If you have any questions, we can discuss them in class on Friday. Make sure to be safe out there, have fun, do a lot of physics, and don't forget about your lab reports. I'll see you guys on Friday.